This video covers search and sorted rotated array with duplicates. I will be solving it with binary search. So first, let's visualize our sorted rotated array with duplicates. There are different cases. So the most trivial case is when we have increasing sequence and then we reach the maximum. After that there is another increasing sequence. So in the most simple case we have a element first is greater than the last element, and somewhere in the middle there is a pivot is maximum and minimum. The other cases are when we have a sequence which starts, has a set of equal elements, and then it starts growing, then maybe it has another set of equal elements until it reaches a maximum at some point. And we have a minimum somewhere here where it also has a number. It may or may not have a number of repeating elements, duplicates, and at some point, again, there are two cases. One is it reaches the point which is below our first element, or another case when it reaches point equal to that case. So this is case number one, when we don't have repeating elements, duplicates. This is case number two, when we have duplicates. However, the most interesting cases are the case number three, when we have duplicates, and not only that, the first element is equal to the last element. There are a couple different cases here. So one case, let's take it like extreme. So let's say we have a list of equal elements until some point. After that we have a minimal element, and we have certain sequence, and then we have a like series of duplicates until the last point. So first, last. So another case is when we have a set of equal elements, then we have a growing sequence until it reaches the maximum, and then we have again like list of duplicates like that. Alright, so actually there are a couple of cases even with that, so we can visually represent them like that. And like that. And like that. And the reason for this kind of sequence is representation is because we will be using binary search, and in binary search what happens is we need to split our array into two. We take the middle central element every time, and in this particular case let's assume when we start we take our middle element right here, central element. So, and as it's obvious that we are not clear where we are in this case, so in which particular part. So the only thing we know that the current element is uh, is not greater than the first element, is not lower than the last element, and we just don't know where to go from that. So um, let's consider a couple of cases. So first, let's consider when we take the first case, this case. So if we take this middle element, the only thing we can do here is to shrink the space, and we do this by moving our right boundary index one step closer right here, and we do it every time, and after that we calculate our, of course, middle element. However, in this particular situation, nothing changes with respect to m. So we will keep moving, and every time m will be actually lower, will be equal to left and right elements. And at some point here, we will reach to the point where if we don't check the right element, we will reach to the point where it will become, we will skip our pivot point, and R becomes greater than L, and from that on we won't be able to find the pivot at all. Okay, so let's take a step back and just think about, so like, why we are talking about this particular case. So overall, the algorithm in sorted rotated array is pretty straightforward. So what we need to do is, first we need to find a pivot element. As assumed here, it is maximum, and after that, second step, we need to check our target. If our target lays is greater than the first element or equal to the first element, what we need to do is to search if our target, let's say we have an array like that. If our target is greater than the first element, we know for sure that there is in this array the maximum element somewhere here, and we have its index. So we know for sure that our target, if it is greater or equal than as the first element, it lays somewhere here. Should be somewhere here. Special case, if it's like equal to first element, there is always possibility that the array looks as one of these. However, in this particular case, when we are asked to find a target index, if it is equal to the first, we just return the first element. So this simplifies this equation that we need to look for element which is greater than the first element and somewhere lower or equal than the max element. So with that in mind, again, so we have this 0 starting index, IDX max is final index for this part, and we just use binary search on the use binary search from 0 to max IDX. Okay, so what happens if it is lower than the first element? In this case, just search with binary search from max IDX plus 1 to the length of an array nums. Okay, so binary search actually doesn't have any complications and any differences with traditional binary search in the array with no duplicates. And the reason for that is we just need at least one index, any index of the element that is matching our target, or -1 if it is not. So those binary searches will return target index, and the only thing we need to do is to compare that it is target IDX is greater or equal than 0. If that's the case, we found that the element does exist. Depending on the task, we can even return that index. However, the most interesting part, of course, is the finding the pivot. Okay, so let's look at several particular cases. First, what we want to check is like check 0 when we are in the binary search cycle, that the R is counterintuitive, but we need to check that actually R doesn't have a neighbor that is greater or lower than the current element. So basically we are looking for the pivot at the R point as well. It's important, and this is major difference from the binary search. So the like 0 check, you just check if say our array n is 1 1 1 1 1 2 1 left, right, and indices are like that. So we check that our n r minus 1, if it is greater than nr, then we just return r minus 1. So and with this check, we can actually check for both cases. We can check for this case. So as soon as we reach r here, as soon as r reaches this element minimum, we will return r minus 1. If so if in this case r reaches this side as well, we return again. So r minus 1 will be greater than r element, and we will return correctly maximum in this case as well. Okay, so what other cases? The other cases, of course, the proper cases. So first of all, we need to calculate median L plus R divided by 2. And what we are checking actually, let's take a closer look. So we have a sequence of elements, let's say right here. So what we want to check that by chance we are either here or here with m, and we are checking it with actually two checks. So first we need to check n m minus 1 is greater than n m. However, actually here, before we check that, we need to make sure that our m is do some sanity check that m is greater than 0. So we can check that by using something like m, or like 0 less or equal than m minus 1, and then this. So in that case we return m minus 1. So next case is when we have, so this is so if the m actually is here, so in that case we need to check that the next element, actually we are not crossing the m is not last, so we are checking it with m plus 1 less or equal than len n minus 1, and that you can put it here r as well, it will work, but just for simplicity. Alright, so m and m plus 1. So in that case we return m. Okay, so third case when the m's element is strictly greater than strictly greater than the L element. So start somewhere here, we are growing an L, and our m lays somewhere here. So what we want to check that we want to check that our element n0 is strictly less than n m. So in that case we know that we for sure are somewhere in the first part. So in that case what we do, we move our pointer left boundary to the next element. So let's assume we were somewhere here. We already checked this position, so we checked with this equation, this inequality. We already checked that we are not at the maximum, so we are either at one step before, one element before, or after one element from that. So we are for sure somewhere here, and in that case again, so we know this is not maximum, so for us it's safe to move L to the next element after M somewhere. This is what we do with that guy, and of course we need to check that if M's element lays somewhere where it is lower than the last element, and it is somewhere here in between of that. So we know for sure that M, we already checked that the previous element is not maximum, So we know for sure that we are either the one element to the right, we are either here or anywhere in between. So with that, it is safe to move our R to right after, right before M element. Okay, so we do this by checking that N, R, or okay, let's N will be len N. Okay, let's N minus 1 is greater than N M, and in that case we assign error M minus 1. Okay, and the final case, of course, when we are unsure, so it's not the greater than the first element, so it's not the greater than the first, so it's either equal to the first, and it is not the greater, not the lower than the last. So it means that this is one of these cases. This other medium element is here, or extreme case, of course, the M element somewhere right there. But the point is we don't know, and the only thing we can, the best thing we can do here is to shrink the space by 1 and continue our, like checks. And in that case, so the final case, we just move our right boundary to the left by 1. And that's it. So those are 6 checks we do until we have L is equal or less than R. We repeat this procedure, and in this procedure, if we do not return element either from here, by definition, this, by the way, this is the, of course, the pivot function. By definition of the pivot function, we need to return max, so in that case it means that array was constantly increasing, or it was something like that. So in that case we just return the last element, return n minus 1, and the last element will be, in that case, guaranteed to be the maximum. Right, so how does it look in the code? So how the solution looks like? So the solution looks like this. So we have a pivot maximum element. Of course, we check for some extreme cases. We first check that, that if we have this kind of array where the first element is lower than the last element, we have already sorted array, so we just return the last element, and then we assign L and R right here, and we find a minimum, this guy, and then we perform all those 6 checks. And 6. Right, so the binary search algorithm is straightforward. I'm not gonna cover it in this video, and we take the maximum element and we check first we of course check if the target element is equal to the first element. We can do, by the way, we can do this check even before you try to find pivot. Yeah, in case of like array of full duplicates, it will be the optimal. And then we check if the target is greater than the first element. So it's that means if the target is greater than the first element, it means that it is between 0 and somewhere max, and we find it as binary search. If it is not, we have to search in the second half of the array. Right, this is an algorithm. As you can see, this algorithm doesn't use only constant space. So the space complexity of this algorithm is O1 or C constant, and the time complexity is if array is has a very few duplicate elements, it will be O log n, and if array has significant amount of duplicates comparable with n, the worst time complexity will be O n. That's it for now.